Okay then, we'll start with the transmission lines, and this is third chapter. So, am I audible for everybody? So whatever the concepts we have studied in the wave propagation, and all those concepts once again it get repeated here. Something like propagation constant, velocity, impedance, all these things will be repeated. The same concept whatever we have studied here, it is going to be applied in transmission lines also. First of all, let us try to understand what is actually the transmission lines meant for. Whatever we have seen in the wave propagation, the information is propagated in any lossless mediums in the form of electric field and magnetic fields. So when I was talking about the transmission lines, the energy propagates in the form of voltage and current. So suppose I can give you some simple examples for the transmission lines. You would have been seen outside the electrical cables, all the power lines which are carrying a frequency of 50 hertz. All the 50 hertz power lines, and even in your coaxial cables, and your optical fiber is also a kind of transmission lines, right? So but actually what happens in a transmission line, the energy is getting transmitted from source to the destination in the form of voltages and current. Now I had a basic question, because when the information is propagated in the form of voltages and current, the analysis is simple. You are going to use your Kirchhoff current law and Kirchhoff voltage law. And what actually there is a speciality. Now, why we need to discuss all these transmission lines? In other words, what is the actual basic difference between the network theory, what you have studied in your academics, the same voltage and current you studied in your networks, and the same voltages and currents we are going to study in the transmission lines. But actually, what is the main difference? Can you tell me what is the main difference? Anybody? There actually, if you remember, in case of your network theory, the voltages and current you have studied for a lumped elements. I think you would have been known what is the difference between lumped and distributed. So especially whatever you have seen in your network theory, you have confined your discussion up to lumped elements, something like resistors, inductors, and capacitor. But actually, when I speak about transmission lines, which are meant for energy propagation at high frequencies. So when you are going for the high frequencies, the energy propagate in a transmission line can be characterized by the distributed elements. So what is the basic difference between lumped and distributed was, in your network, suppose if you design a particular network, something like this, RLC circuit, which is actually present there. Whereas in case of a distributed elements, when I say transmission lines, that inductance you may not be able to see it physically, but still there is an inductance associated with that. And similarly, across the two conductors, there will be always a capacitance, which you are not directly seeing it. And at the same time, when I say distributed nature means basically, so if you have a transmission line, consider it is a two-wire line. So suppose if I was giving a 100 volts of signal at the source end, and my length of the transmission line is sufficiently high compared to the wavelength. So what will happen to the signal when it reaches the destination? Can you expect the same 100 volt will be present here? So can you answer? If my length of the transmission line is very huge, and if I was applying a voltage of 100 volts at the source side, you expect 100 will be exactly reaching the destination. That is basically said to be the distributed nature. So when I say distributed nature, as the distance, if the wave travels for a certain distance, the wave will get automatically attenuated. So in case of a distributed network, the voltage varies as a function of distance. Similarly, your current is vary as a function of distance. Which means if your source is supplying 10 ampere current, by the time it reaches the load, only 1 ampere reaching the destination. So the distributed is basically says that the voltages and currents are continuously going to vary as a function of distance. And what happens in a lumped elements, because in your network theory, you have assumed that the length of your element or the resistor or the length of the inductor or the length of the capacitor, you have assumed that it is much, much lesser than the wavelength. And especially at low frequencies, you have confined. At low frequency, your wavelength is very high. And if you see your resistor element, the length of this resistor element is quite negligible when you compare it with the wavelength. That time what will happen, as long as the signal propagate on the length of this conductor, you can't see any attenuation because it looks to be flat because your length is very, very small. What will happen if length is much, much higher than the wavelength, especially at high frequencies, you are going to get an attenuation. So the conclusion here was, in a lumped elements, the voltages and current are going to be assumed constant throughout the length of that particular element. So whereas when you see in the transmission lines, the nature is distributed. So which means that voltage and currents are varying as a function of distance. So have you understood what I'm saying, everyone? So if you have any questions, you can share. So which point you want me to repeat? I said only 2 points here. Yeah, distributed element means if the length of the element is much higher than your operating wavelength. Suppose if I have a transmission line, my length is meter. Let us say the length of the transmission line is 10 meter. And if I was passing a frequency of, let us say, 100 megahertz. 100 megahertz means, can you tell me what is the wavelength? The wavelength is in the order of 0.3 meter. In that case, what will happen? Your length of the transmission line is much, much higher than your operating wavelength. So what will happen in this case was, when you feed some input here with a certain level, let us say 100 volt, because the length is very high, your attenuation factor is going to be significant. Okay, so what will happen till now in second chapter you have seen, the wave gets attenuated with a factor of e minus j beta l. So e power j beta l means 2 pi by lambda. So that can be L by lambda. If suppose if your length is very, very small compared to the wavelength, that is basically said to be the lumped element. So in case of a lumped element, L is much, much smaller. So this term is going to become 0. So L by lambda can be neglected. So you are going to get exactly equal to V, and this factor is equal to 1. And what will happen if length is much, much higher? If length is much, much higher, you cannot omit this factor. This is going to be a significant factor. So in that case, what will happen? As the length increases, you can see here, this is dominating. The wave gets attenuated with increase in the distance. So that is what distributed nature says. So in case of a distributed, because your length is much, much higher than your wavelength, the wave is getting attenuated as it propagates over the length of the transmission line. That is not the case when you are seeing in the lumped elements. Understood? Yeah. So you can see here in this diagram, there are the different type of transmission lines are existing. So you can see here, this is a coaxial cable, which is basically used in your television applications. And the communication happens in the range of megahertz, you can say typically. And this is your two-wire transmission line. Just now I have seen your power line. And this is your high voltage transmission lines, electric lines. And this is your multi-layer circuit board. Even in case of a PCB, you may have a different traces running over it. So one will be the high line. You can see the microstrip line, you would have been studied about it. So there will be a microstrip line, and with respect to ground plane. So this is actually carrying the forward wave, and this is the return path. So this is also a kind of transmission line. But anyhow, we are not going to discuss this. Microstrip lines is a special case of microwave engineering that we are not going to cover as per the gate syllabus. So first we will start with the parallel wire, two-wire transmission line. So when you see the two-wire transmission line, first of all, what will happen? This is your one conductor and this is your another conductor. So when you take a two-wire transmission line, here you are going to apply a source, and let me say this is my load. Now the first question here, if I want to analyze how the voltages currents are going to propagate in this transmission line. So as I said, in case of distributed, the voltage is a function of distance and current is a function of distance. Now if I want to analyze what are the equations or how the voltage and currents are fitting in a transmission line, the first thing what you need to do is, whatever the physical existing for this transmission line, you should be able to represent in terms of your electrical model. The reason because you can easily analyze voltage and current in a electrical circuit model. So that is the reason why whatever the physical transmission line existing here, if you are if you are able to model it in terms of a circuit modeling, then you can apply your KCL and KVL and you can easily see what is the voltages. For that, first I would like to analyze the electrical representation of the transmission line. So when you see the electrical representation of the transmission line, okay, first thing, what all the elements it consists of? This is basically a conductor and this is also a conductor. So the current is flowing in this particular fashion and takes the return path through the other conductor. So since the current is flowing through a conductor, so every conductor is having a finite amount of resistance, correct? So the conductor is going to have a resistance, and what else you are having? So when any current is flowing through a conductor, there will be some magnetic field generated. So that magnetic field, whenever there is a concept of magnetic field, obviously there is an inductance associated with that. So in addition to the resistance of the wire, you are having a inductance of the wire also because of the time current which is passing through the conductor. Yeah. And similarly, you can see here the current is flowing in this direction and takes the return path in the opposite direction. So we can assume that if this conductor is positively charged and the return conductor is said to be negatively charged. So what will happen in this case? This is a positive conductor and this is a negative conductor. In between there is a dielectric medium. So there is a capacitance here. So there is a capacitance across these two conductors. So that I can model it as something like this. This is my capacitor. And of course, this dielectric material, if you are talking about ideal dielectric medium, what is the resistance offered by the ideal dielectric? Can you answer? If I say ideal dielectric medium, what should be the resistance of that? Resistance should be infinite, correct? But practically, when you see the reality, you are going to have a dielectrics which are non-ideal. So which means that your resistance is very high, but it is not going to be infinity. So whenever that dielectric is having a finite resistance, what will happen? When there is a current flowing through this conductor, if the dielectric offers infinite resistance, there will not be any leakage current. That is basically you are calling it as a dielectric loss. The same thing I was telling it here. So if it is non-ideal, what will happen? There will be a finite resistance offered by this, of course, which is very high. So there is a small amount of this current, whatever is flowing on the conductor, it will flow through the dielectric medium. Basically, that is said to be the leakage current. So if the dielectric is non-ideal, that is going to have some kind of conductance, I can say, which is the reciprocal of your resistance. So because of the conductance offered by the dielectric, there is a small part of leakage. So that also I have to include in my model. So that actually completes my electrical circuit, right? So when you see here, throughout the length of transmission line, you are going to have a number of RLGC sections like this. So this is a equal for a small part. You can distribute like that. So since it is said to be distributed network, these circuits is going to be repetitive, something like this. Now I can replace this physical model with this electrical model. Is it clear? That's what I have shown in the next slide. If you see the diagram, your input and this is your output, and the entire length of the transmission line, you are going to have a section of RLGC sections like this. You are going to have a number of this one. So whatever we have discussed here in this circuit is for a small section. So if the length of the transmission line is more, you can cascade this number of sections together. So that's what you can see here. So this is how it is going to represent in terms of circuit model. So once again, I can repeat, this arc is the contribution of your conductor resistance. And L is nothing but, because you are passing some current through the conductor, you are going to have a magnetic field effect. So that can be accounted by adding a series inductance. And similarly, this G, why I have added circuit was, if it is an ideal dielectric, you can simply neglect the value of G. But since all the dielectric are non-ideal, so there will be a finite amount of conductance. And this capacitance comes because you are having a, if you see the diagram, you are having a current flowing in the upper conductor, takes the return path as the other conductor. So one will be positively charged, other one will be negatively charged. And between that, there is a dielectric medium. So there is a capacitance here. So is the model clear, or any point needs to be discussed here? So have you understood the model? Yeah, good. Now, there is one interesting thing here everybody has to notice. What is the unit of this R, L, G and C? These are basically said to be the primary constant of a transmission line. So when you see the manufacturer specifications, so suppose if you buy any coaxial cable and if you see the manufacturer specifications of that, they will resist 100 ohms per meter. So they will always mention resistance, inductance and the capacitance. All these values, they will define per a unit length. So suppose what I mean to say, if a coaxial cable, if you are purchasing for 1 meter length, you may have a resistance of 20 ohms per meter. So suppose if the same kind of dielectric and same kind of material, and you are having another coaxial cable of 2 meter, in that case also they will mention 20 ohms per meter. What is the actual difference here? This 20 ohms per meter represents for 1 meter distance, the overall resistance is 20 ohms. But in the second question, what happened? In the second case, for 1 meter it is 20 ohms. Since the length of the transmission line is 2 meter, the overall resistance will be 40 ohms from one end to the other end. But what the manufacturer is always used to mention for transmission line was per unit distance, what is the resistance and what is an inductance. So if we see the units, that will be in ohms per meter and Henry per meter, and conductance is in mho per meter and capacitance is in farad per meter. The reason being why it is mentioned per unit distance was, as I already said, the transmission lines are said to be. So all these primary constants are basically depends upon what is the overall length of the cable. So as the distance increases, the overall resistance also changes. So in order to make a generalized relation, so they will mention all these primary constants with respect to unit distance. So don't get confused. Though the name indicates resistance, since it is said to be distributed nature, the resistance is mentioned per unit distance. And similarly, L, G and C. Clear? So that is what the primary difference. If you are characterizing any lumped elements, straight away you can say the resistance is 20 ohms. Whereas if you are characterizing any distributed model, you should always categorize the resistance as per unit distance. So 20 ohms per meter or 30 ohms per meter. So that is what the basic difference between your lumped and distributed. Okay, don't get confused. So all the so whatever the primary constant I have mentioned here, all are defined with respect to the unit distance. Okay, this anyhow will continue in the next class. Okay, this is I thought I can give an introduction for the transmission lines today, and we'll see in the next class. So this part, have you understood what I meant to say, everybody? Yeah. Okay, we'll do the analysis part in the Sunday class. Actually, Friday there is no class for me. He has not scheduled, and my next class is there on Sunday. Okay, so do the practice for the wave propagation first, and once you're done with that, and be ready for the transmission line class. So next we are going to discuss a complete new topics. So come up with a fresh mind, and whatever we have discussed till now, so we had almost like 4 days time before the next class. So try to complete that part and be ready for the next class. So the transmission line theory is very important, and this chapter is very easy. If you see the gate problems, it's not like your static fields and your wave propagation. It is very simple, and the concepts you need to understand. Okay, so I think I request you can sign out now, except those people who are having the doubts. Now if you have any doubts we can discuss, or else if you don't have any doubt you can sign out, other people.
Sir, about those
Yeah.
questions which I had sent on WhatsApp, shall I forward the same images again?
Hello.